So we will looking at conditional density functions. Conditional distributions conditioned on certain events. So you can condition the density or cumulative distribution function of a random variable based on a condition that is derived on some events or on some other random variable. We will look at both these things. That is, you have a sample space and then a random variable x being defined as mapping from some events to real axis, and you have the density function of x being given fx of x denoted as fx. Now if we have an event here as a, and if you are told that the event has occurred, with this how do you recompute the density function? That is called as the conditional PDF denoted as fx of x given a. Okay, this is the conditional PDF. Now what we can do is, instead of taking one event, let us take a partition. That is, by a partition we mean the set of events a1, a2, ak, okay, which are all subsets of the sample space, such that they are mutually exclusive. And connectively exhaustive. Then you have again the same random variable x, which is being well defined on this sample space. Of course, on the event space, on the sigma algebra defined over the sample space, the probability measures are given, and using which you come up with the density function. Now you can find the conditional density function of x conditioned on which one of these events. That is, we can compute f of x given a I x, f of x given a1, let us say a1, a2, and so on. Each one you can find out. How do you generally find it out? What you do is, for any x value which has been let from a sample point present in a1, for example, how to compute a1? I am giving it little in a verbal manner. If there is any value of x for which you want to compute it, if there is a sample point that maps onto this x, then only we are told a1 has happened, which means only a sample point within a1 has been realized. Then x the random variable can only take those values which are mapped from the sample points belonging to a1. Other values are not possible. So for those, the probability of realization of those values, if it is a continuous one, any range in which those values fall, they are all will be 0. Okay. So for those values of x which are mapped from the sample points of a, there is a measure is there. But to normalize it, all those probabilities measures we have to divide it by 3 of a, then it will be normalized. So this is how we do to get the conditional density function of x given a1, x given a2, and so on. Then it should be very clear that the fx of x, if you want, I can write it as fx of x given sample space of x. Which means it is same, because this condition doesn't add anything. It said a sample point in the sample space would have occurred and it is always true. So this condition doesn't impose anything beyond what is already given here. And we can always say this as and we know that A1, A2, AK are a form of partition, their intersections are 0. So if you put a condition, they all will be, they don't have an intersection. So you should be able to understand that we can write this as okay. That is what we do is the unconditional density function of x is the conditional density function of x for different events and then multiplied by weighted by the corresponding probability of occurrence of those events and then add it up everything and you will get this. This is a theory of total probability in one sense. There are total various ways in which you could come up with. This is one wherein the density function comes and then the probability of an event comes. So this is one thing. Now, suppose that you want the other one, f of a I given x. Okay. Sorry, x is less than or equal to x, something like this. That is, in this manner, density function can be found out. Even conditional cumulative distribution function can also be derived in a very similar manner. So, you know that given an event A1 has occurred, what is the density function of x? Now, given that x takes some value over a range, this is one range, minus infinity to x. You can specify other ranges like a to b and so on also. Okay. Or let me put a to b. X takes a value between a to b. What is the probability that even a1 would have or a2 would have is the other question. This is a posterior probability. These are prior probabilities. What you are given is, given a1 or a2 or a3 are occurred, what is the corresponding density function of x and so on. And therefore, these properties can be found out using this one. By integrating between a to b this one, this property will be given. Those are the properties given a1 has occurred or given a2 and so on. Now you ask me reverse question. Given that x lies between these two, what is the probability that a1 would have occurred or a2 would have occurred? Then how can you write this one? This is a given b. So I can write it as probability of a1 intersection another event, that is, there are two events, a1, ai, so ai, as well as this one, a given b can be written ai and this event divided by probability of is it clear? A given b is a intersection b by b. The same thing we have extended it here. Only thing is, instead of b, we are instead of the condition, we are here it is the condition on the random variable taking some values in some range. There will be a corresponding event in the sample space which would have given rise to this one. Instead of mentioning it that b or some other event, we are mentioning it in terms of the random variable. That's the only difference. Now what we can do, how we can write this one? This can be written as right? Now we can of course multiply dx on both sides. Okay, not dx, okay. Okay. So this is how we can calculate. See, these are all okay. Look at this one. This is what this. What is this one? This is fx of a and b, is it? Okay. It's from this is what it is, right? Correct? So now this is for some between a and b. I could also write a and x plus dx. That is nothing but fx of x into dx. So in general, what I can do is I can always write fx of x given ai of x into p of ai divided by fx of x. That is x given ai of x into p of ai by fx of x. So what here we are doing instead of here, so this is one way. In an infinitesimal, another way is like this one is again here I will put okay. I have to prove, okay, yeah, this is here I can put dx, then it will become the same probability. Okay, I can put dx, then it will translate it to probability it will have. So we can always write it in this manner. Again, what is this one? Fx of x. Fx of x is this one. So we can write it as fx of x given ai of x into p of ai divided by this one can be written as sigma I varying from 1 to k f of x given ai of x into p of ai. If I want, see, this is a dummy index, this is a particular index. If it is getting confused, I can change it to j. And here it is nothing but that is, given that x takes a value in the neighborhood of small x, what is the probability that aj is the event that would have occurred can be found out using a form like that. That is, conditional density function of x given aj into p of aj divided by the unconditional density function, which again can be written like this. How does this form look like? This form should be familiar. We have an analogous formulation in the earlier probability theory. It is Bayes' theorem. So this is nothing but the continuous form of